Previously, we've been looking at calculating the instantaneous gradient of a function. If I have a function, I look at a single point, what is the gradient at that point? Or what is the gradient of the tangent at that point? They're the same thing. And what we did is we chose 2 points and then we moved one closer and closer to the first point until they're essentially the same points, and we are finding the instantaneous gradient. It's a very subtle but clever technique. That gives us an instantaneous gradient, and we got the instantaneous gradient in terms of x. So however x is changing, it will tell us what the gradient is. We can substitute in for x to get that. This process is known as differentiation. I didn't bring up that word before, but this is the topic we're now studying. And what we're interested in today is to get a rule for polynomials, because we've seen that if y is equal to x squared, dy by dx was equal to 2x. Y is equal to x cubed, dy by dx is equal to 3x squared. And we proved that using this, this idea that if y is equal to f of x, then dy by dx is the limit as h tends to 0 of the rise over the run. Whoops, that was a mistake. So you need to be able, essentially, to, given this definition, to be able to prove these. But actually, that's just one part of it. If we can find some rules, then we can also just then use that from then on. Okay, and that's what we're going to have a look at now. Let's try and find a rule for polynomials. So polynomial will be things with x squared, x cubed, x to the 4, and even adding them, or even 2x squared plus x cubed plus x, for example. But actually, although I've called it a rule for polynomials, we go beyond that because we're also going to be looking at x to the half or x to the minus 2. These are actually not polynomials, but the rule will still apply to them. Okay, let's do this. How are we going to get a rule for polynomials where we're interested in x to any power? Well, let's put it into the definition, x to the n. That's the function I'm interested in. So then f of x plus h is going to equal x plus h to the n. Now that does not look very nice because I don't know what n is. How am I going to expand it like a double bracket or a triple bracket? I can't. However, we can because we actually know the binomial theorem. So provided n is equal to 1 or 2 or 3, etc., nice whole number, we can use the binomial theorem. And that becomes, we call this nc0, x to the n, plus nc1, x to the n minus 1 times h. This is a reminder of this theorem, plus nc2, x to the n minus 2, h squared, plus all the other terms. We're going to have a lot. We don't know how many terms we've got, but actually I'm going to show you it doesn't matter. So we're going to see that dy by dx is going to equal this thing here. Now I just need to work these out. Actually, this one is just equal to 1. So it's x to the n. This one is just equal to n. So it's n x to the n minus 1 h. This one is actually n, this one gets a bit more complicated, n factorial over n minus 2 factorial x to the n minus 2 h squared. Just going to delete, just going to make a bit of space now. This is not essential. And then we've got the other terms. I'm not actually, and actually it goes all the way up to h to the n. That's my last term. And then I need to minus x to the n. So all of this bit that I'm now kind of going over is this thing here. But I still need to minus my x to the n, which is this bit here. And then I need to divide by h. And although this looks really complicated, sorry, I also forgot to put the limit in. I was rushing it. H tends to 0. Right, now look what happens. Just like before, these cancel out. I was trying to do it in a different color. These cancel out. And then, just like before, the h's cancel. Now, I'm not going to factorize the h out. I'm going to use this other method where I can basically cancel those out. I can cancel this down to h. This is going to become n minus 1, etc. I've got lots of terms. But if I let h tend to 0 here, then this term is going to tend to 0, but all the other terms are going to tend to 0, including this one, because I'm timesing by h, which is tending to 0. And all I'm going to be left with is n x to the n minus 1. And this is a proof then, when we've got x to the n, that dy by dx is actually n x to the n minus 1. What a simple formula. We simply multiply by the power and then reduce the power. That's it. Now, a little warning, we've actually not proven it for x to the half because we can't use the binomial theorem in this case. Actually, there is a binomial theorem that you can apply to fractional coefficients. You've not studied it yet, so you're just going to have to trust me for now, but it works out in exactly the same way, in fact, and this works for any value of n. I've only proven it for some values of n. You're just going to have to trust me for the rest of them. And here's the overview, actually, okay? This is the one I've just shown. This needs to be written down and learnt. We just multiply the power by the power, reduce the power by 1. This is true for any real number. This means these are my numbers on my number line. We've spoken about those already when we covered surds and different number types. So basically, any number in A-level maths, essentially. Okay, I didn't prove this one, but if you have a constant multiplied by x to the n, then the constant just passes all the way through. Like you keep it there, and then you just multiply by it at the end. So that is also another absolutely essential one to learn. And then there are some special cases. They still fit into the rule, but they're a bit more confusing. If y is equal to a constant, then the instantaneous gradient is 0. Now, let me explain it from an understanding point of view. If y is equal to a constant, then this is what the graph looks like. It's just a straight line. So of course the gradient is 0 everywhere. But if you want to use the rule for it, and you can, then what you would actually have to write down is y equals, you'd have to write down y equals c x to the 0. X to the 0 is just 1. But now I can put it into this rule here, okay? That means that dy by dx is going to be c times 0 x to the 0 minus 1. If I just use the rule, and if I multiply by 0, then you see I get 0. Now I would recommend you don't use the rule for this. You just learn that if you have a constant, when you differentiate, when you find the instantaneous gradient, it just disappears. Okay, and the other one is a little special case, is kx. Now actually, kx is simply this line here. It's our y equals mx plus c line. And so obviously, if it's kx, that's the same as mx. It's just going to give me the gradient. The instantaneous gradient is just a constant. It's a constant gradient. It's not changing. If you want to use the rule, then it will be y is equal to kx to the 1. And then when I do dy by dx, I will do k times 1 x to the 0 when I'm minus 1 from it. And again, these will just cancel and I'll be left with k. So again, I'm giving you justification. These still work with the formula. It's just that they're in some way, they're the ones that you're most likely to get wrong because you'll just forget to get rid of the constant, for example. Now, so I've spoken about dy by dx. I've spoken that this is the same as differentiating. We call dy by dx the derivative. It's just a slightly different word for it. And another bit of notation is f dash x. So these are the same thing. Dy by dx is the same as f dash x when y is equal to f of x. And one other thing that you will see is that sometimes I don't write dy by dx. I write things like this. D by dx of x squared equals 2x. So I just get rid of the y completely, but I can still use the rule. So expect all of these things to be seen. We also call dy by dx the gradient function, or the instantaneous gradient. So that's some notation. Okay, this is absolutely critical. Being able to get to the rule is important. Actually, I would say really important, because it's the understanding. Now, learning the rule at this point is even more important, because it comes up all across maths A level. It's absolutely everywhere, including a lot of second year content. Next year, in second year, you'll learn how to differentiate things other than polynomial functions. So you can see this is like the introduction to differentiation. But anyway, these are the rules. They work for any value of n, and we're now going to have a look at applying the rule essentially. Right, here are some questions on differentiating. What I want you to do is write them down, try each one, try one, and then watch my little solution to it. Try one, watch my little solution. This is the first time you've done this, so it's absolutely fine if you don't know how to do one, but I'm giving you the opportunity to figure them out, okay? So here goes, try the first one. Right, if we use the rule, and it's up here, but I'm going to just keep it in the back of my mind now. I'm timesing by the power and reducing power. Actually, I think I will just, I'll bring it down just so it's here. Okay, just so I can keep referring to it. Right, now all we do is we times by the 10, we reduce that 10 power, and it becomes dy by dx is 10x to the 9. And that's it. What about this one when I've got a constant in front? Well, I times by the 4, I lower the power, it becomes minus 20x to the 3. This is fact. This is the instantaneous gradient of minus 5x to the 4. If I've got a quarter, I do the same again. Now this is where it gets a bit trickier, because you have to know how to do a quarter minus 1. It becomes 5 times a quarter, which is 5 over 4. And then a quarter minus 1 is actually minus 3/4. You can do that in your calculator, but I would be expecting you to do it without a calculator, in which case you either know it, or you have to do a quarter minus 4 over 4 after you've made a common denominator, and that gives that minus 3 over 4. All right, the fourth one's a bit trickier. What you have to do for this one is you have to write it in the form of a polynomial, or sort of x to the power of something. So it's 7x to the minus 3. So well done if you realize to do that. Actually, I've said this before, your indices and your surds, they'll underpin a lot of the maths you're doing. So once if you just look at it, this is really horrible. You might make it 7 over 3x squared, but no, that's not what the rule says. The rule's got very specific. It's x to the power of something. There's no, you're not dividing by x at any point. If I do that, I'll get minus 21x to the minus 4, because I'm minusing 1 from minus 3. Okay, so yeah, get x up from the denominator is the key thing. It's the denominator. I don't want it as the denominator, so I write it like this. Next one, dy by dx is y is equal to 5. That's your special case. It's just 0. As soon as there's a constant, get rid of it. Okay, next one's a bit tricky. Right, we don't have it as x to the power of something at the moment, but we can do it. We can write it as x to the 1 times x to the half. Again, you need to know your fractional indices. You add them together, you're going to get x to the 3 over 2. That's what 1 plus a half is. And then it all falls out. 3 over 2, x to the half. Bring the 3 over 2 down, minus 1 from the numerator. So change surds into fractional indices is the key point here when you're differentiating. All right, next one. This is very similar to some earlier ones, but now I'm using different notation. I'm still saying I want to differentiate it, okay? And the answer, I bring the power down, I reduce the power 20x to the 4. Next one, same sort of thing, just different notation. Differentiate 7x. This is what this is saying. So 7x is my second special case. I just get 7 as my answer. All right, now there's one thing I've not said so far, and this is crucial for this case. When you have different polynomials like this, actually you just differentiate each term separately. So what I'm saying is if y is equal to f of x plus g of x, then dy by dx is equal to df by dx plus dg by dx. I differentiate each one. You can actually prove that. I'm not going to prove it here. I'll leave that as a challenge for you. But basically, if you're adding functions, you can just differentiate them separately, which is great because it just means we just have to differentiate three things. So what did you get for this one? Well, the first one, I bring the power down, subtract it, it's going to be 15x to the 4. The second one, I times by 3. I'd write that as 3 over 2. Always write it just as a fraction, improper fraction. I wouldn't write it as 1.5, to be honest. The last one, again, I've got to be able to deal with my thirds. This is 6x to the third. So I multiply through by a third. I'm going to get minus 2. And then when I minus 1 from a third, I'm going to get minus 2/3. Sorted. Okay, this next one, got to think carefully about it. You cannot differentiate it as it stands because it's not x to the power of something. So first of all, you have to write it, you have to simplify it. So it's going to become 6x to the 5 divided by 2x squared plus 3x over 2x squared. You have to do this step first. And now you can simplify this down. It's going to become 3x to the 3 plus 3 over 2 x to the minus 1. I've done that quite quickly. I'll talk about it just a little bit more. Yeah, these are going to cancel to give me 3 and 1. I'm going to subtract my indices to give me x to the 3. Over here, I could write it as 3 over 2 times x over x squared if I want an intermediate step. And then again, I subtract my powers, and it's going to give me x to the minus 1. And that's not my answer. That's just me writing y in the correct form. And by the way, I think after you've not done this topic for a while, this is the one that you'll make a mistake on. You'll try and differentiate the top and differentiate the bottom, but you can't do that. We've not proven that. That rule doesn't exist. Here's what you get. You differentiate. We're going to get 9x squared minus 3 over 2x to the minus 1. So be really careful here. I've times by minus 1, and then I've lowered the power to minus 2, but hopefully you're happy with that. Okay, last two. What is the gradient of the curve 2x plus 3 squared when x is equal to 5? How are we going to deal with this? Well, we don't have a rule for this. So first of all, we're going to have to multiply that out. We're going to have to multiply a bracket. It will become 4x squared plus 12x plus 9. That's a double bracket that you should be confident at expanding now. And what do we get? We get dy by dx. Oh, sorry, I've done the whole thing there. Dy by dx in terms of x is going to be 8x plus 12. That's my dy by dx. So the grade, remember, this is the gradient along the whole curve. So if I want the gradient at a specific point, I just substitute in 5. 8 times 5 is 40, plus 12 is 52. So expand brackets and simplify first, differentiate it, and then substitute a value in. So you will need to be able to find that that is actually the gradient on that curve. Amazing that we can just figure that out through this very simple rule. All right, and the last one. Okay, this is maybe the most difficult. This brings in some previous topics even more so. Find the points on y equals 1/3 x cubed plus 1/2 x squared minus 2x, where the instantaneous gradient is 4. Well, first of all, we need to differentiate it. We need to find the instantaneous gradient everywhere. So I'm going to do 3 times 1/3, that cancels. I lower the power to x squared. I'm going to do 2 times 1/2, that cancels. I'm just going to be left with x. And then minus 2x becomes minus 2. So what I want to then do is set this. I don't need to write dy by dx anymore, actually. I'm interested in the values of x where the gradient is 4. So it's going to be x squared plus x minus 2 equal to 4. And guess what? Quadratics are back. I form a quadratic. I just need to solve this. X squared plus x minus 6 equals 0. Remember, we always set it equal to 0. We've got 3 methods for solving. Expect it to factorize for this sort of question, or at least try to factorize it first. We're going to get x plus 3, x minus 2 equals 0. So x equals 2 or 3. It does say the points, so I think we should technically... oh wait, I made a mistake there, sorry. The points. Oh, it's not really that clear whether it means the y values as well. But you know, if you asked for the coordinates, you would get the y values as well. To be safe here, you might substitute in to get the y values. But the main thing I'm interested in this question is to get the x values. So that's it. I mean, I know we've done quite a lot there. I've gone through these examples. Hopefully you've tried them yourselves. This is just a little extension. Can you think of a function which, when differentiated, gives itself? I'm not going to talk about that in this video, but I'm just going to summarize. We've now got a rule for differentiating y equals x to the n, even y equals kx to the n. We've got these two special cases. We can then just apply this rule in lots of different situations. We've got to be aware of all the different types of notation that there are, f-x, d by dx, calling it the instantaneous gradient, etc. And we've got to be able to deal with situations where it's not in the form x to the n. We might be dividing by it, we might have surds, we might have both, we might have brackets, we might have divisions. We have to do these extra steps in those cases. We might even be asked to find the values of x where dy by dx is equal to something. Plenty of practice needed on this topic because this is stage 1 of stage 2 of differentiation. We've shown where these things come from. Now we've learned the rule, but there's lots more to learn. So practice, practice, practice.